Hello and welcome. Simple harmonic motion dynamics. This question is gone into one of my further mechanics papers. Dynamics is with SI terms basically when you have to consider forces and derive usually the equation of motion. I don't know if you can see the question here has been cropped up, unfortunately. A particle P of mass 0.5 kilograms is attached to the free end of a light elastic string of natural length 0.8 meters and modulus of elasticity 90. The particle is in equilibrium, hanging vertically from a fixed point A. Okay, and then the particle is pulled vertically downwards a further 0.5 meters and released from rest. Show that the subsequent motion P moves with simple harmonic motion. Okay, a lot of information here in this particular question. So what we're going to do is I'm going to record some of this information here. So first of all, mass of the particle 0.5 kg, light elastic string, natural length L 0.8 meters, lambda modulus of elasticity 90 newtons. The particle is in equilibrium, hanging vertically from a point A. So basically what we've got is some kind of ceiling, and this is in the equilibrium position. So that's L, and this extension, equilibrium extension is E. I'm going to mark some forces on the particle, and the objective of this part here is not part A actually, it's just part of the part A, is to actually find an expression for E. So this is the tension, Hooke's law, and this is the weight of the particle, mg. And I'm going to do some mathematics very, very quickly. So first of all, tension must be equal to mg. By Hooke's law, lambda over L times the extension, which is E in this time, is mg. So the extension is which I'm going to record. It doesn't really matter. We can't put the numbers. I have a calculator actually with me today. So FGL is what's M 0.5 times 9.8 times 0.8 divided by 90. It's probably just a very ugly number. Almost 0.8. It says 49 over 1125, so it's in meters. I recorded this bit here. So what I found so far is I have found when it's in equilibrium, lying there undisturbed, the extension on the string, and how big is that, is about 4 centimeters, just a little bit over 4 centimeters, is exactly that. Okay, and now I'm going to go to prove that the particle will be moving with us 8m if we pull it a little bit further down. So the question says the particle is pulled vertically downwards a further 0.5 meters and released from rest. So this is the equilibrium position, and this, of course, is 0.5. And where will I mark the particle? The particle will be marked in some arbitrary position. It's not there. I'm not interested in releasing or marking the particle when it's at the very far end and is moving. So it's an arbitrary position, a random position in motion. So motion has been taking place, let's say, for some kind of split second. And again, in this position, we have forces. This is mg. This is the tension on the string. But now, this 0.5, let me just mark it. Let's mark it here. It has some significance, this 0.5, but for what we're about to do next, we really need to be marking other things in the picture. Let me just get a different color pen. Let's say we get this blue pen. This particle now, where I marked it, is at the distance x below the equilibrium position. Okay, the next thing is something that a lot of people have an issue with. I definitely had an issue when I first saw it in my textbook. I had to teach myself maths at A level, and it wasn't explained. I mean, it was a diagram like that, and it was x like this. X double dot was marked downwards, and I thought to myself, yes, I can see if you mark it like this, everything works, but why is the acceleration downwards? I mean, after all, if we're to pull the particle down here and we release it, clearly it should be accelerating upwards. Why am I marking the acceleration perversely downwards? And my students as well, they have exactly the same issue, but now I understand the problem, and of course I jump in there before they even ask. Now, this is not physical acceleration like a physicist will consider it. If you have, let's say, a particle, and this is the direction of x increasing, so that's the plus x, so we're measuring x in this direction. This is the direction of x double dot, velocity, and this is the direction of the acceleration, second derivative, acceleration, because of course this is where x is increasing. Everything else, if you mark it correctly, calculus will take care and everything will come out in the wash. You don't want to be marking the acceleration upwards, because then you'll be pulling your hair with other things, because other things need to change directions. Okay, so we are returning now to the equation of motion. I'm going to write here F is equal to ma, basically, or shall I say, because normally we write it ma is equal to F. So in this particular case, as we have it here, mx double dot, mass times acceleration, is the net force in this direction. So in this direction we got mg downwards minus the tension, and we're putting our things in. The tension is of course lambda over L times the extension. The extension, careful, if the particle is in this position, the total extension in the string is E plus X. Okay, so by Hooke's law. So in this particular case, I could put my numbers, but it will actually, this will always happen if you're measuring the X from the equilibrium position. Things will cancel. So let me show you what I mean by that. So I'm multiplying the bracket, this will be a minus in there as well, lambda over Lx. And remember, on the side, I have an expression for E. I left it like that. I know the numerical value as well is, in fact, what is it equal to? Is equal to lambda over L bracket mgl over lambda minus lambda over Lx. This cancel, and if you see what happens, the mg's will cancel. So, which is equal to minus lambda over Lx, and we can divide by m, and this actually suffices to show SHM, because of course this is a positive constant, and for SHM the equation is x double dot is equal to a minus some positive constant, and to show it's positive we write it as omega squared x, which of course has some significance. And the center is where x is measured from. So in this particular case, let's put the numbers in. Minus, we got 90 divided by 0.5 divided by 0.8. What does that give me? 90 divided by 0.5 is 180. 180 divided by 0.8 is 45 times 225. So it's actually a nice number because it's a square number. So definitely SHM about equilibrium position, because that's what we're measuring x from, and with omega, the angular frequency, the square root of the number, and that's what I said, it's a nice number, is actually 15, the square root of 225. So the part A, to show that P is moving with simple harmonic motion, if we do that, is done. Okay, what does the second part says? The particle is next pulled vertically downwards a further distance a meters below the equilibrium position and released from rest. So this time we pick the particle and we pull it down a distance a below the equilibrium position and we let go again. We know there's nothing special about a. The same way it was 0.5 there. It will still be moving with simple harmonic motion. If the particle passes through the equilibrium position with a speed of 3 meters per second, calculate the distance P covers until it first comes to instantaneous rest. Let me explain a little bit first of all, before I draw a diagram again if I need to for the part B. First of all, this is the amplitude. So for the first part of the problem, where we're pulling about 0.5 from the equilibrium position, this represents the amplitude of simple harmonic motion and is partial at SHM. So let's mark it as A. It's not 0.5 anymore. We move to part B. But what will happen, if you think about what is happening, is being released from this position with, of course, no velocity. It will reach maximum velocity at the center of the oscillation, which is here. So I'm going to write here Vmax, because that's what the 3 represents, because it does say if it passes through the equilibrium position with speed 3. Okay, and then we'll start slowing down until this point here. What happens there? The string will become slack, so the motion, the SHM motion, is now interrupted. The particle, however, has vertical speed upwards, and therefore it should move under gravity up to a certain point. It'll come to an instantaneous rest, let's say somewhere here, and then it will start dropping back down. At this point, it will be recaptured in speed marks by the string, and then we will re-enter an SHM motion from here, center of the oscillation, extreme of the oscillation, and the same cycle will repeat. So the question now is to find the distance that the particle covers until it first comes to instantaneous rest. Let's say that position's up here somewhere. So from there to there. All right. It doesn't tell us how far we pulled it down for the second part of the question, but it's not difficult to actually compute that, because of course there is a formula in SHM which says Vmax is equal to A omega, and of course 3 is equal to A, and omega, the SHM, is independent of magnitude. Okay, if you look at the angular frequency, which turned out to be 225, I rubbed it off now. I can't quite remember what it was equal to. I think it was the omega turned out to be lambda over ml, and this turned out to be 225. That's what, oh sorry, the omega squared. If you look at the omega, does not depend on the amplitude. It depends on the lambda, which is exactly the same. Modulus of elasticity depends on the mass of the particle, still 0.5. It depends on the natural length of the string, still the same. So therefore, this bit here is still 15. And therefore, the amplitude is 0.2. So what we have done so far is we know for the SHM from here to here, okay, it will be SHM amplitude at 0.2, omega is 15, and so on. So we can do some kinematics. What do we want? We want the displacement. I'm going to use the formula V squared is equal to, do I need this one, or shall I just be going for the time bit? What's the best way? No. What I'm going to do, I'm going to first of all consider from there to there. That's a quarter of the period, because I'm after time. So going from there to there, quarter of the period. So quarter t, the period's of course 2 pi over omega times a quarter, and that is pi over 2 omega. So that's pi over 30. So that's how long it takes to move from release until it reaches the center of the oscillation. Then I need to know how long does it take to move from there to there. If I set the standard SHM equation where the time measures from the center of the oscillation, these are standard formulas. X is equal to amplitude. If I measure from the center, sine omega t. If I was measuring from the end, is cos omega t. So in this case, that is 0.2 sine of 15t. And this position here, okay, is a displacement of E. And the displacement of E is this disgusting number, 49 over 1225 is 1/5 sine 15t. The sine of 15t is equal to, using the calculator, these just ugly numbers now, that times 5, so that's 49, so I've been able to do that in my head, but I didn't. Make sure your calculator is in radians, a big must in all SHM questions, and since we're looking for the first positive solution, I don't really need to write a proper trigonometric solution, it's just the arc sine of that. I'm in radians, sine to the -1 of that, it'll give me 0.21953 ... and therefore t, if we divide this by 15, divide by 15, syntax error, what did I do wrong? Put 2 divides there by mistake, divide by 15, I got 0.014635 ... So let's collect our results so far. This time is quarter of the period, time it takes to go from there to there. This time is a little bit like 4 centimeters. I'm expecting some tiny little number. And of course, after that, I need to do kinematics. So under constant acceleration, under gravity. So I need to know what speed does the particle have there. So the way I will do that, first of all, I need to do v squared is equal to omega squared, a squared minus x squared. My intention is to find when x is equal to e, what is the v that goes with it. So v squared is equal to omega squared, which is 2 to 5. A squared is 0.2 squared minus e squared, where e is this bit here. It will take me a little while to compute all of that. So first of all, 49 that to 1125 equal, square it, equal 0.04 minus my answer, equal, times 2 to 5 equal, so let me just write something down, 8.57, 31 ... and therefore v, when it reaches that point, is the square root of this number, which of course is 2.92799 ... So lastly, I've got to do some kinematics. Now the particle is at this point, so I have u, a, s, t, and v. So I'm starting with an initial of 2.92799, subject to an acceleration of -9.8. By the time I come to instantaneous rest, what is the t that goes with it? Which equation is that? That's actually quite easy. Is actually v is equal to u plus at, and this I've done the question wrong all the way. Oh my god, calculate the total distance. It's okay, I'm doing calculate the total time. Yeah, you can see if you don't read the question, you do extra work in here. I just want to show you what I've done in there. If the particle passes to the equilibrium position with speed 3 meters per second, calculate the distance the particle covers until it first comes to the distance. I'm doing the time. You might be wondering why I'm finding all these times now. I'm fairly retarded. I'm awfully sorry. I'm having a bad day. So oops. I'll do the distance afterwards. I'll redo, or not redo the question, redo parts of this question. So this is what we got. 0 is equal to 2.92799 minus 9.8t, and therefore my time is that divided by 9.8, which is 0.29877 dot dot dot. And therefore, if you ask me how long does it take to go from there to there, the answer would have been that plus 0.14635 plus shift pi divided by 30. I would have made it a total time of 0.418 to 3SF. I hope at least I've done it correctly. So here I misread the question, or rather my brain's very cloudy due to medication at the moment, and I kind of like read the question the way I wanted to read it. So let's do the find distance. So all of this now is not really, and I rubbed off this bit as well here. Omega squared is m lambda over ml equal to 225. This is still okay up to here, but then I got into a time calculation. My deepest apologies. You can see it can happen to everybody. This was not planned. It's gonna make the video extra long and so annoying. Okay, let's return and collect our thoughts. It's actually a lot easier to find the distance, because the distances we have, first of all, the distance is from there to there is A, from there to there is E. We have A, 0.2, we have E, 49 over 125. All we need to know is what's this distance here. So first of all, I'm going to use V squared is equal to omega squared A squared minus X squared for SHM in order to find what speed I have here at this position here. So V squared is equal to 225. And as well, I had this number. I computed this number in the previous calculation. I don't remember it now. Oh, God. Okay. It was 2.57 or something, but now I can't remember it. Okay. We got V squared. Now, I'm going to start with this. That's 49. 49 divided by 1125 is equal to that. Square it, equal to that. 0.04 minus answer, I work this out, times 35 equal, V squared is 8.57315. Yes, I remember the number. That was what I got earlier on. So this one, now when I square root it, is in fact 2.92799. So what I've worked out is when it's about to come off SHM and go into free fall, this is the speed. So now kinematics, U, A, S, T, and V. U is 2.92799, acceleration minus 9.8. By the time the velocity is 0, not what's the time that goes with it, but what's the S that goes with it. And the equation for that is, of course, V squared is equal to U squared plus 2AS. 0 is equal to this squared, which is that. Minus 19.6 S, that's two lots of 9.8 negative. And if I use my calculator for that, I get that the displacement from there until I come to rest is in fact 0.4374 dot dot dot, and therefore the total distance is 0.4374. This is 0.2. This is 49 over 1225. And assuming I haven't made any silly errors into this, let's add a 0.2 first of all. That gives us that, plus 49 divided by 1125. I got the answer to 3SF, a total distance of 0.681 meters. And I do apologize about the mishap during the video. I hope you followed. I got more stuff than I needed. I misread the question. And I hope you found this useful for SHM. And it did help you understand the motion a little bit better. Okay, I'm going to be signing out as this video has gone very, very long. I'll see you real soon. Bye for now.